Okay, so thank you. I will present the work of my PhD student, Gabriel dos Santos, and we are playing with data layouts to improve performances, and it might be of interest to you. So basically, we are in a world where performance portability is a need, and it's not this easy to obtain. In Kokkos, you have this mdrange policy we talked about yesterday, where you have this tiling parameter. So you iterate on parts of your data. So you have this two levels iteration. So the idea is to maximize performances by using more efficiently the cache on CPU and having a better mapping on GPU. So basically, all multidimensional objects are still stored in a 1D memory, and we can choose how we will iterate on this memory. So we can iterate by rows, by columns. We can do weird things like Z-curves, iteration if we want to try to optimize the data temporal locality. But traditionally, and it's the case in Kokkos, the data we stored are flat. So you choose layout right or layout left, but they don't. The data are not tiled. But our iterations are tiled. So what we wanted to try is to do the opposite. So to tile the data and to run with a flat iteration and see how it works. So we have implemented in mdspan custom layout to store the data like this. So this is a right tile right. So it means that the layout inside the tile is a right layout, and the tile are also organized following a right layout. And we have implemented the other combination, and we have done some performance tests. So the idea of the implementation is just to define this mapping from the multidimensional space to the linear storage space. So for regular tiling, we can express this with this formula, and we can do this for any ranks of the multidimensional array. So this is what looks like the code. So it's not a lot of code to implement this. And I will spend a little bit more time on the experiments we have done. So we took a very classical kernel, so it's a gem. We implement this as a very naive kernel. So we are using mdspan here, not Kokkos, so that's the reason why on CPU we have just used OpenMP for threads parallelisms. And we wanted to see the results. So the lower curves here, it's not very readable, but is the naive approach. So the performance at the beginning are decent, but when you increase the size of the matrix, it begins to drop because you don't fit the cache. If you use this, the blue curves are when we change the layout. We have a better performance, but we still have a drop at the end, and we will explain why. And the red and the yellow curves named CB are the cache blocking curves. So it's what mdrange does, for example. So why we have a drop in performance using the tiling on the layout is because we recompute again and again the offsets, and it's quite a lot of computation comparing of the one of the kernels. So if we look at the number of instructions, we see that we have a dramatic increase in this number. So even if we are better at using the cache, we perform too many computations that are not useful for our kernel. So the idea is now to combine the cache blocking and the layout tiling. So currently, it's not easy to do with C++. We don't have this kind of external indices where we can mutualize the mapping, in fact, outside the data structure. So I will present a bench where we have done this by hand, just to see if it works or not. So the code looks more complicated because now we have 6 loops, but the offsets in a tile are computed only once, and after we iterate inside the tile, and the computation is a lot more easier. And these are the performance we obtain. So at the bottom are the previous performance from the slides, and the 2 new curves. So there is this violet curve when we choose a large tile, and we don't really fit into cache. It's not perfect, but it's still already a lot better in performance. And when we switch to a tile of 32 by 32, where the 3 matrices can fit in the lowest level of cache, we have a dramatic increase in performance. And here also the curve is pretty flat. So there is I think it's 64 speed up between the naive approach and this approach. So I think it shows that it's very important to be able to shape correctly the data and the algorithm. So it's not something very new. Kokkos has shown that it's important to link the data layout and the kernels, but I think we have to go a little bit farther, and we have to put the tile inside the layout to exploit efficiently the runtime tiling, the cache blocking. So summary is we have this custom tile data layout for mdspan. So it's not public yet, but we will make it public. It's just paperwork to do, so it's long. And and it has a dramatic impact of performances. And in the future, we want to try this on GPU. So we will use the Kokkos provided mdspan implementation. And we have begun to test on other kernels. So for example, on Stencil, where you do less computation than with a gem, we have a 3 times speed up comparing to the naive approach. And we will welcome any idea of usage for this kind of layout. And we will do more experiment on GPU and try more advanced layout. So thank you.
All right, do we have some questions? I see one, and okay. Yeah.
Do you think it's better to tile the algorithm, or do you think it's better to tile the data?
I think you have to tile both, in fact.
Okay, but okay.
And so it will depend on the problem. On some problem here, we show that at the beginning it was better to tile the data. But if the problem gets bigger, it's better to tile the algorithm. So it's better to tile both and to both the tiling agree in size. And that's the reason we want to explore Z curves. It's to be less tied to the problem usage.
We have another question. So can we just switch laptops and then you can answer the question while we do that? Perfect.
Oh, hey. Hey, great talk, Cedric.
Thank you.
Yeah, one of the approaches that we take for our matrix multiplies is to leave the matrix in its user-defined layout and then to load it in a different layout so that the small tiled matrix multiplies are more efficient. Is that something that you've explored?
So we have not explored that. What we wanted to show is that the layout has an impact on performance. But yeah, I know that Bliss, for example, works like this and have this hierarchical approach to design custom layout for each level and end up with great performance. But we wanted to be less tied to algorithms.
Okay. Yeah, thank you.